I'll start with Williams, Edward Williams will be talking about effects of lunar lava tube shape and dimension on internal failure and external observability. So Edward, if you could try to share your screen.
Oh, okay, thanks. Sorry, let me just get my PowerPoint in the right.
And I'll also note that co-author is Montesi.
Sorry, I'm just trying to share my screen properly. Okay,
all right, we can see this. Yes, and Wajiha, can you reset your clock? All right, you're good to go, Edward.
Okay, thanks. Sorry, I'm just trying. Okay, so hi, I'm Edward Williams, and I've been studying the internal usability and surface observability of lunar lava tubes. So just for some background and introduction, lava tubes are long subsurface void spaces left by lava flows. They exist on Earth, and we also have evidence indicating that they exist on the Moon. A lunar lava tube would potentially be an ideal environment for exploration or habitation on the Moon in the future. So the goals of this research were to model lunar lava tubes to determine their internal stability and how they can be located and studied from observable surface features. So some of the evidence that we have indicating that lunar lava tubes exist include observations of sinuous rills, which are winding troughs on the lunar maria. These are believed to be related to lava tubes since they have related formation mechanisms, and they can be connected to lava tubes or contain tube segments. We've also observed holes on the lunar surface, which we think are skylights into lunar lava tubes. And also we have gravity data from GRAIL and ground penetrating radar data from this lunar radar sounder, also indicating that lunar lava tubes exist. So I've been using finite element COMSOL multiphysics 2D models to simulate lava tubes. I used an idealized lava tube shape that you can see here on the right, which is a half ellipse with a width-height ratio of 3:1 and a rounded corner. I varied roof thicknesses and tube widths, and I determined regions of different types of failure on the internal surfaces of the tubes and on the surfaces above the tubes. This was for my main models. I also did some model variants using different tube shapes. I changed two aspects of tube shape, which were the width-to-height ratio of the top half of the tube and the floor curvature. The width-to-height ratio of the top half I changed from 3:1, which was the original shape, to 6:1, which was a flatter version, and 2:1, which was a semicircle. And the floor curvature I ranged from a flat floor to a semicircular floor. And I found the maximum tensile floor stresses for these tubes of different shapes and compared them. I used an elastic rheology for my models with a shear modulus and Poisson ratio that you can see here. I used plane strain assumptions, and my models are simply loaded by gravity with the density of the material and gravitational accelerations that you can also see here. For failure criteria, for tensile failure, I just used a cutoff at the tensile strength of the rock. And for compressive failure, I used the Hook-Brown failure criterion. These needed strength parameters, including these needed parameters, including the GSI, or geological strength index, and other strength parameters for the rock. You can see the values that I found were calculated for these in this table here. So this is an example of one of my model results. The sort of dark blue to white shading is showing how close the rock is to compressive failure. And it's white where the rock is in compressive failure, although this doesn't actually occur in this model. And shaded red is showing where the rock is in tension, and the red circles are showing tensile failure on the roof and floor of the tube. So I found, I studied several different types of failure inside these tubes, the most extensive of which was tensile failure on the tube floor. I found that this was present in all but one tube, and wherever it was present, it covered most of the floor, over 65%, and in some cases covered almost 95% of the floor. I also studied tensile failure on the tube roof and compressive failure on the tube wall, because I found these three types of failure were found to be present inside the tubes. And the combination of these effects meant that most of the floor was interrupted by cracking or debris and was difficult to use, and it was expected to be difficult to use. I characterize usable floor as any region of floor that isn't interrupted by cracking and isn't directly underneath any region of roof that's failing but could be dropping debris onto it. I found that the maximum usable floor extent for these tubes was 500 meters, This was generally greater in shallower tubes, but did not depend predictably on tube width. Also, additional factors not captured in these models could cause further failure to occur. These are the results of my models with different tube shapes. I found that increasing the curvature depth of the tube floor decreased the floor tensile stress and made failure less likely, and increasing the width to height ratio of the top half of the tube increased floor tensile stress. You can see this plot, the y-axis is showing the maximum tensile floor stress. The x-axis is the floor depth, and the different colored lines are showing the different top half shapes that I used. So that was what I found for the internal failure inside the tubes. I also studied the surface features created by the tubes on the surface above them. I found that each tube is expected to cause two regions of tensile stress buildup to either side of the tube. These are expected to be highlighted by tensile cracking. I calculated the distance for each tube from the center of the tube to the location of tensile surface stress. I found this distance depends predictably and linearly on tube width and tube roof thickness. And this relationship could be used if we can find this surface feature to determine the width of the tube from the surface. I also studied a similar distance, which is the distance from the center of the tube to the peak of the elastic bulge that it causes on the surface. And I found the ratio of these two distances to be constant. I think this ratio could be used if we can find these two surface features, but if we can't find the tube itself, to determine the location of the tube. As well as my modeling, I also did some observations of the lunar surface using the LROC QuickMap tool. I looked at LROC imagery and other available data sets. I studied sinuous rills and surrounding areas where I thought lava tubes might be present. The results were that in most locations, I didn't see thanks. In most locations, I didn't see the expected clear linear cracking patterns that I was looking for. It's possible they were present but undetectable due to regolith buildup, degradation over time, or just that they were too small to detect this imagery. However, there was one location where I did see the kind of linear cracking patterns that I expected, which was the southern end of Rima Myran. I found two lines of cracking that continue the path of the rill and connect two large O-line depressions, and I think this suggests that the rill continues into a tube. So this is now my discussion of my results. I found that I think my findings about usable floor regions inside the tube could have multiple different implications for future lunar missions. They could constrain the sizes of planned lunar bases, and also since I found usable floor region to be only near the edge of the tube, this would mean that if we entered the tube through a skylight and arrived at the center of the tube, we would need a way to traverse over a damaged floor. Also, since the usable floor regions near the edges, direct overhead access to a skylight for things like solar power will be impossible. So we need to find some sort of way to work around this. Also, a method of clearing debris from the floor would be useful. And inflatable structures, if they're used, should be reinforced to account for the large amounts of debris and cracking expected that may have sharp edges. Also, since I found that usable floor extents were larger in shallower tubes, if we can determine the roof thickness of a tube from the surface, such as from angle imagery, we could use this to prioritize choosing shallower tubes to explore. These are the surface feature relationships that I described earlier. I think these could be used if we can determine the surface features to study the tubes, as I described earlier. And my results about tube shape, I think also could be applied to future lunar missions. I found that the most usable floor is present in tubes with curving floors and low width to height ratios, so these may be preferable to choose. However, there are also drawbacks to choosing a tube with a curving floor, since a flat floor may be more advantageous for walking on or constructing things on. So I think both of these factors should be taken into consideration when choosing a tube. And finally, I found a candidate lava tube extension of Rima Myran at its southern end. I used the surface feature relationships I described to calculate an approximate width for this tube of 200 meters. I think relatively little failure is expected in such a small tube. And I think other such candidate tubes could be found in the same way in other rills or using other data sets, or possibly in the future using higher resolution observations from the lunar surface itself. And here I have just a summary slide of my conclusions. Thank you for listening. Are there any questions?
Thank you, Edward. It looks like there are a couple of questions popping up in the chat. I'll read out the first one, which is Ichi asks, why do you think the source of Rima Myran Myron, a lava tube rather than the surface expression of a dike instead?
Oh, right. I guess I was thinking that for one thing, it struck me that it's sort of the fact that it connects these two aligned large depressions, and the large depressions sort of follow the same line as the cracking does. I was sort of actually I was making me think that if this were, the depressions would also fit with if this was indicative of a tube, because it could be that the tube is partially collapsed, which could also explain that sort of oddly shaped depressions.
All right. Well, thank you. Oh, go on.
I was just going to say that also it was very similar to the sort of patterns that I was expecting to find in my research, so that seemed indicative of a tube to me.
Well, very interesting.